Engineers, insurance analysts, economists, rocket scientists, and the list goes on, all use mathematical modeling to describe real-world events that occur in their respective fields. Hi, my name is Tom Atwater, and today we're going to be investigating mathematical modeling. Let's start with the most basic type called the numerical model. The following table shows the percentage of female and male populations in the United States employed in the civilian workforce in selected years from 1954 to the year 2004. Here's the table. We have the year, the female percentage, and the male percentage. And let's just take a look at this so that we can get an idea of what's going on. As we look at this model, we can see that if we look at the female percentage, it appears to be increasing, except for maybe this has a small dip from 99 to 2004. If we look at the male is decreasing, then it increases right here. Then it goes to decreasing, increases there, and then decreases again. So at least we have some idea of what the trend is by simply looking at those numerical models. Now, let's go on to a couple of questions that we have. For letter A, according to the numerical model, what has been the trend in females joining the workforce since 1954? And as I said, we found that it was increasing, except 1999 to 2004, there was a 2004, sorry, there was a small decrease. So really, overall, we can say that the trend was for it to be increasing from 54 up to 99, and then a small decrease from 99 to 2004. Okay, part B says, in what 5-year interval did the percentage of women who were employed change the most? And I will tell you that in examining it, you will find from 1974 to 1979 that would have been the greatest increase in the percentage of women being employed. And again, that's simply a matter of looking at that numerical table and comparing each of the intervals. Okay, next we're going to look at algebraic models, which use formulas to relate variable quantities associated with the phenomena being studied. The added power of an algebraic model over a numerical model like the one we just did is that it can be used to generate numerical values of unknown quantities by relating them to known quantities. So let's take a look. Here's an example. A garden shop sells 12-inch by 12-inch square stepping stones for the same price as a 13-inch diameter round stone. If all of the stepping stones are the same thickness, which option gives the most rock for the money? Okay, well, what we need to do is compare then the area, because the thickness is the same. We want to compare the area of the square to the area of the circle. So to do that, we know that the square stepping stones are 12 inches by 12 inches, which means their area is 12 squared, or in other words, 144. And that, of course, would be square inches, but since we're dealing with the same units for the circle, we don't worry about that. Circle is pi r squared, and r is the radius, which is going to be half the diameter. And when we multiply all of this out and convert pi, I should put approximately 132 and 665 thousandths. But what we can clearly see, though, is that the area of the square stones is larger than the area of the circle, and therefore the square stone will give us the most stone for the money. Next, we're going to look at a graphical model, because that's a visible representation of either a numerical model or of an algebraic model, and it will give us insight into the relationships between the variable quantities. Learning to interpret and use graphs is a major goal of this textbook. Let's take a look. A physics student obtains the following data involving a ball rolling down an inclined plane where t is the elapsed time in seconds and y is the distance traveled in inches. Find an algebraic model that fits the data. And we have the data here for t. And of course, we have intervals 0, 1, 2, 3, 4, 5. And then the distance it's traveled is given by y. And what we want to do here is enter those two lists into the calculator. And when you enter those two lists into the calculator, and then you ask it to perform a plot, you will get this plot here, which at first glance, you may or may not recognize that, but it does have somewhat of a parabolic shape to it. What I would say is you could think of it as this half of a parabola, which would then continue over that way. And so therefore, we would want to run a quadratic regression, which I've done here. And you can see by running the quadratic regression, we come up with an quadratic equation, which is 1.2 x squared. And that is an example of a quadratic regression coming up with the algebraic model from the visible graphical model. Well, let's revisit a property that's going to be useful in solving equations algebraically, and that is called the zero factor property. And it tells us the product of real numbers is 0 if and only if at least one of the factors in the product is 0. Let's look at an example of where we would apply this to solving an equation. Find all the real numbers x for which 6x cubed is equal to 11x squared plus 10x. The first thing we're going to want to do is rewrite this as 6x cubed minus 11x squared minus 10x equals 0. And we should now see that there's a factor of x in each of these, so I can factor that out. And I am left inside the parentheses with 6x squared minus 11x minus 10, and that all equals 0. Then I can factor this quadratic, and the way that factors is into the two binomials that we have 3x plus 2 times 2x minus 5, and that equals 0. Okay, and next I'm going to go off to the next screen and finish this problem off. So here we go. What I have, remember, is x times 3x plus 2 times 2x minus 5 equals 0. And that zero factor property tells us that if we're multiplying these three numbers and they have to equal 0, at least one of them has to be 0. In other words, x equals 0, or 3x plus 2 equals 0, or 2x minus 5 equals 0. Well, I'll repeat this answer, x equals 0. This answer gives us x equals negative 2/3, and this one gives us x equals positive 5/2. All right. Well, now we have solved equations graphically by using the graphing calculator, algebraically, which is pen and pencil like we just did here. But the graphing calculator also has an equation solver that allows us to enter the equation itself and have the calculator solve it without graphing. We call this solving numerically. Every method of solving an equation usually comes down to finding where the expression equals 0, as in this example. If we use f of x to denote the algebraic expression in the variable of x, then the following connections can be made between finding those zeros and with f of x. And that is this. If a is a real number that solves the equation f of x equals 0, then these three statements are equivalent. The number a is a root or a solution of the equation f of x equals 0. The number a is a 0 of y equals f of x. And 3, the number a is an x-intercept of the graph of y equals f of x. Sometimes the point a comma 0 is referred to as the x-intercept, or, as I said, just the number a is the x-intercept. All right, great. Well, let's look at a 4-step problem-solving process that we can follow when we're attempting to solve a problem. Step 1, understand the problem. Make sure that you know what you're being asked, as well as what information is being given that's helpful in solving it. Develop a mathematical model of the problem, and that could be using the graphing calculator as we did when we found the quadratic regression. Step 3, solve the mathematical model and support or confirm the solution. And finally, interpret the solution in the problem setting so that it applies to the actual problem that you were asked to solve. I think the best way for us to see this in action is to apply it to a particular problem. So let's do that right now. The engineers at an auto manufacturer pay students 8 cents per mile plus $25 per day to road test their new vehicles. How much did the auto manufacturer pay Sally to drive 440 miles in one day? And part B, John earns $93 test driving a new car in one day. How far did he drive? So what I'm going to do is stick with part A first. And part A makes use of the information that it's $25 a day plus 8 cents per mile, and Sally drove 440 miles. I think I understand the problem. I've got the information I need, and I know what I want to find. So the second step is to come up with the mathematical model. And in that case, I'm going to call it P for how much she's going to get paid. And I know that she starts off with $25 per day, plus she earns 8 cents times, and I'll just use X to represent miles. Well, in Sally's case, we don't know how much she's going to get paid, but we know it's 25 plus 0.08 times 440 miles. And when we work that all out, we'll find out that she was going to get paid $60.20. So that example is where we came up with the model P equals 25 plus 0.08x, and we were given x as 440. But now for part B, the part with John, what we were told this time is that he received $93, and we need to figure out what x is. So to do that, I just want to erase Sally's work and make some room for me to set up John. And so what that would look like is this. $93 is how much he earned. The 25 is given per day, and it's 0.08x. And so I subtract 25 from each side, and I'm going to rearrange this to say 0.08x, and that's going to equal 68, and then divide both sides by 0.08, and I come up with 850 miles. So that's how far John drove to earn his $93. All right. Well, after reading the problem, I understood what it was I was looking for. I didn't need a diagram in this particular case because it wasn't going to help me. And then what I did is I designed the algebraic model that P equals 25 plus 0.08x, and then I worked out Sally's pay, which was $60.20, and then John's mileage worked out to 850 miles. Well, now it's time for you to try a problem. And the problem I want you to solve is this. Swan Auto Rental charges $32 per day plus 18 cents per mile for an automobile rental. How much did Elaine pay if she drove 83 miles in one day? And part B, how far did Ramon drive if he paid $69.80 for one day? Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Okay, let's find out how you did. After reading and understanding the problem, again, a diagram isn't going to help, but what we want to do is design the algebraic model, and the algebraic model this time is that the cost, which I'll use as C, the cost is equal to $32 per day plus 18 cents per mile, and I'll use X to represent my miles. Well, what about Elaine? Elaine, the cost was $32 plus she drove 83 miles. So it would be 0.18 times 83. And when we work all of that out, it'll turn out that it cost her $46.94. All right, well, now on to Ramon's mileage. Well, remember, Ramon paid $69.80, and we want to figure out how many miles that is. So let me do this. I'll turn to this and say $69.80 is how much he paid. The model is still the same, 32 plus 0.18x. I have to subtract the 32 from both sides, divide by the 18/100ths, and what I'll find is that x will be equal to 210 miles. So that's how far Ramon drove in that one day for which he paid the $69.80. Well, I hope that's the answer that you got when you worked out that problem. Great work today's lesson. So in today's lesson, we looked at mathematical modeling and then how to solve those mathematical models when they apply to real-life situations. Be sure to work the exercises that your teacher assigns, and we'll see you next time.